electron beam and the diffracted electron beam from the sample. As an individual atom column acts as a scattering unit, so the diffraction frequency is actually the atomic frequency. But that's one set of imaging. And on the right, I'm showing a scanning transmission mode where we make the beam itself a very small size, of a very small size, say less than an angstrom, and then we scan across the sample, and each atom column acts as a scatterer, and based on the scattering angle we get different types of information from the sample. So here I have shown a detector which is known as ADF detector, annular dark field detector, which actually captures only those electrons which have been scattered at very high angles. So what's the usefulness of this is that the scattering cross section is proportional to z square, where z is the atomic number, and so the image is actually the image contrast is actually proportional to z square. And then if there are two types of atoms present in two or more types of atom present in your sample, and if they are occupying different positions at the unit cell, just directly from the image you can interpret it. All right. So the scattering probability as a function of distance, inverse distance, is presented here. So the oscillating scattering cross section is from the HRTM, and almost a linear cross section is from ADF stem. So as you can see, the images from HRTM sometimes become it can give us it passes through plus and minus. So sometimes it passes through 0. All right. So if the lattice planes fall in these distances, then we don't get any information from them. So this problem doesn't arise in ADF stem. So in other words, in a nutshell, the high resolution TEM images are not directly interpretable, but high resolution ADF stem images are directly interpretable. So STEM is not only good in that, the another thing where STEM is good is that we know where my beam is. All right, so we can use this information to get X-ray and electron energy loss from the incident electron, and we can just combine this information and the spectroscopic information specially to get high resolution maps when we are in STEM mode. All right, so here are some examples of high resolution TEM images. Maybe some of you or all of you have seen these kind of images. So here we definitely get useful crystallographic information, crystal structure information, but these techniques are almost 30 to 40 years old now, and until and unless the samples are beam sensitive, where we cannot use STEM anymore, we still use these high resolution TEM techniques. But most of the materials research, the high resolution materials research, has moved on to STEM because of the advantages that I have told you in the previous slide. All right. So what happened in the last 20 years is that why this STEM, or why this aberration correction has become so much popular these days is because okay, even before that, I just want to tell one thing, that aberration, what does it do is that a point object, just like all these electron lenses are magnetic lenses, so they have aberrations. So if you can see really